Hello, I'm Andrew Dinn from Red Hat's Java team, and I'm going to present to you some details of the debugging capability that I've added to GraalVM native. So let's start by talking about GraalVM, what it is. GraalVM's a project that was started by Oracle some years back. It's primarily focused on polyglot programming, running applications that are implemented in a whole suite of different languages and having them interoperate, including interoperating with Java. You can deploy those applications on top of the OpenJDK JVM, or you can also deploy them as standalone binaries. And the bit that Red Hat are interested in particularly is the GraalVM native part that allows you to deploy programs as single binaries, and in particular we're interested in deploying Java applications as an executable. What that means is that you take all the classes that are needed to implement the application, both the application main class, all the libraries it uses, all the JDK runtime classes, and the native image generator translates them all into a single executable program that contains all the behavior and all the data that's defined in those Java classes. So you can deploy that application on its own as a single installed program without needing to ship the classes and without needing a JDK runtime on the target machine that you're deploying on. In order for that to be possible, the program needs to satisfy what's known as a closed world assumption. That means given the main class and the main method of that main class, it must be possible at build time for the native image generator to be able to work out every class and every class that's referenced from that main class, every method that's invoked from that main method, and do so recursively and identify in all cases which classes are needed at build time and be able to compile the relevant code and data into the program for use at runtime. Now that means there's certain use cases that work on a dynamic OpenJDK JVM on a normal Java runtime are not going to work. For example, if you had a program that read a class name in, read a method name, and then invoked that method of that, loaded the class dynamically, and invoked that method of that class by reflection, that wouldn't work because you don't know in advance which class you could end up calling, and so the code couldn't be built into the final program. As well as limitations on class loading and reflection, there are also limitations of use of method handles. Certain situations where the target of a method handle invocation can't be known. But in many cases, programs do satisfy a closed world assumption, including classes that use a lot of the standard enterprise libraries. In cases where it's not automatically deducible what the target of reflection or method handle operations are, what classes might be loaded, it's possible for you to configure the build for the GraalVM native to make it clear exactly which classes will be found, and in consequence close the world of the application to allow a standalone binary to be created. And in fact, Red Hat's Quarkus product provides exactly that capability for many of the standard enterprise libraries as one of the things it brings to the table when you're running using Quarkus. So why would you be interested in shipping as a single binary, apart from obviously the simplicity of shipping one program rather than a whole lot of class libraries and a Java runtime? Well, there are a couple of really significant benefits that make this very interesting, particularly for containers. When you run things on top of OpenJDK, the JDK runtime has to do a load of initialization in order to cater to the fact that you might throw all sorts of different classes at it during execution. It has to be prepared to load classes dynamically. Now, a lot of that initialization is done in advance. It's not really needed in all applications, but it is needed to make the JDK work. So when you've got a single giant binary executable, you can cut out a lot of that initialization. You don't really need to do it. Also, some of the initialization that's done at runtime with OpenJDK can actually be done at build time because you know it's not going to change from build time to the runtime environment. Both application code initialization and JDK runtime initialization. So that means you can start up and do far less work at startup. And so where, depending on your machine, it might take 1 or 2 seconds to start up a Java process on the JVM, it may take some tens of milliseconds to start up a native image. So that's really important for containers where you're spinning up and down processes much more frequently, and you really want them to be available to answer client needs straight away. Now, as far as object data is concerned, objects are no more compact or smaller on a native binary than they are on a standard OpenJDK runtime. There's not really much room for you to make savings in object storage. Maybe in a few rare cases you can, but mostly not. But what you can do is save on code size and on metadata footprint. So it's possible to get memory savings. When you have a closed world and you know exactly which classes are involved in the runtime, certain bits of code where it's open-ended what might get invoked become determinate in the closed world model, and that means it's possible to cut out some of the branches in code and reduce the complexity, and as a consequence also do some further optimizations because of a fixed range of choices that aren't necessarily available in the OpenJDK runtime. So there is a possibility in some cases of getting reduced code size. The biggest saving is in metadata. The OpenJDK runtime, dynamic JVM, needs to keep track of what classes is loaded and update that class model and use it to revise assumptions about how it's compiled code in particular. So it has quite a rich model of the class base. Most of that is used at build time to compile a native image and then can be thrown away. So you don't actually have anything like as much information about the loaded class base, and that saves you on memory footprint. For programs which are dominated by heap data, that really isn't necessarily going to be very significant. But for small programs, say microservices, which don't necessarily have a lot of object data, that code and metadata footprint can be a significant proportion of the total memory use of the process. So there's quite a significant saving for a deployment that uses a whole suite of microservices, say, rather than a large monolithic program. The downside, well, if you run for a long time on OpenJDK, the JIT compiler monitors what's going on during execution and optimizes the hot paths in code and can throw away code and remove it from the optimization process for stuff that's not been executed so far. Obviously it can repair if that code ever gets executed, but it means it can actually do a lot of optimization over time, which can give you much higher peak performance than a compilation that's based upon no prior knowledge of what the program's going to do. So there's generally better, you're sacrificing peak performance for long running applications. As far as memory management is concerned, if you've got a program that has a lot of memory pressure, either bursts of memory use and then wants memory reclaimed quickly, or is going to use a lot of memory, the memory management in OpenJDK is still far superior to the garbage collector that's provided with the native image. Obviously that's being worked on, but at the moment programs with heavy memory use are probably going to run better on OpenJDK. Clearly that's not the case for container applications, particularly microservices with fairly low memory footprint and low throughput of memory. For container applications, native image is certainly very interesting, and we're very interested in using it as a back-end for Quarkus applications. It works already using GraalVM, although it's not currently supported, but we're working towards that. So what's the problem that I'm looking at, and what have I done about it? When you translate all these Java classes into a standalone binary image, the code is incredibly heavily optimized, and it's very difficult therefore when you're running a bit of machine code to know what it's doing and how it relates back to the original Java source code. So debugging this code is a real problem. Now the same thing happens when you've got an optimized C or C++ program, and that's fixed with C or C++ by adding debug information to the image that relates the compiled program back to the original sources. It tells the debugger that when you're running this code, this is where it comes from and this is what the information looks like, and so on. Now I've done something equivalent to what's been done for C and C++. I've put information about all the method code in as debug info using the dwarf debug information format for Linux. There's a Windows version being worked on, but it's not available just yet. So that means that we've got a fairly good basic debugging capability now for native images. You can do the obvious thing, which is set a breakpoint and stop at a particular point in a file at a given line, or stop when you enter a particular Java method that you've described by name. And you can run up to that point, and then the debugger reaches that point, it'll stop. Then you can step line by line. You can step into a call or over a call. When you're in a call, you can step out to the calling method and finish it. And you can see the stack backtrace whenever you're stopped, so you can identify what series of calls got you to the point where you've actually stopped and broke the program. So there's the ability to actually do a fairly reasonable amount of debugging with this capability that I've added. I'll actually show you that to show you what it looks like and how far we've got. There's a bit more work I'll explain later on that we want to do, but it's already very usable. Now the obvious thing to do would be to debug Hello World, but that's a one-line program. So what I've done is I've built a slightly more complicated version of Hello World that uses some extra classes and extra methods to just print a simple hello greeting message. It's simple enough to debug, but it's going to exercise some of the functionality of the debug capability that will show what's possible. So I'll switch now into demo mode, and we'll actually have a look at that program. Here's hello.java. It's a single class with some nested static subclasses. The action starts down at the bottom here with the main method, which takes the usual string array, and it passes that to a method of class greeter, which is a builder method that creates an instance of greeter. Now greeter is a class that knows how to print a greeting message to say hello. So we call the abstract method greet, and depending on what type of instance we've got back, we'll get a suitable type of hello message printed. Having done that successfully, we exit with status 0 by calling system.exit. So here's the class greeter, and this is the builder method, also called greeter. And that command line string array is passed in, and if there's no arguments on the command line, it just creates a default greeter, and of course that's going to say hello world. If there's one command line argument, then we take argument 0, that value that's passed on the command line, and we use it to construct a named greeter, and it will print a targeted welcome message. If there's more than one argument, we throw an exception, and the program will exit with a non-zero exception return code. The abstract method greet here is implemented by default greeter in the obvious way. It calls system.out.println, so it prints a hello world message to the output stream. Named greeter has a constructor that takes that command line argument as the name and stores it in a local field, a private field, and when its greet method is called, it pastes together a welcome message using the name, so we get a targeted welcome message. So let's run that. I'll show you the classes in the local directory. We've got hello.class and all the nested classes. So all the application source code is in the local directory. So if we run that, Java will find it in the local directory. We can run it with an argument, and it does the right thing. If I give my full name, it throws an exception. So it's all working as expected. Now, what we really want to do at this point is translate that into a single standalone binary that will do the same thing. I'm doing this in a GraalVM source build. I'm in the substrate subdirectory, which is the lightweight virtual machine that's used to replace the JVM. So I'm going to use the mx build command to run the locally built native image binary and to give it hello as the entry class. All the classes are in the local directory here, so it should be able to build the closed world model of the application and then generate a hello binary. So I'll use mx native image. If you had a Graal binary download, you just run the native image that's in the bin directory of that download and give it hello as the argument, and that would generate the binary for you. Now I want it to include DebugInfo, so I'm going to add this extra flag, generate DebugInfo equals 1, using the standard -h option to specify Graal option, and it will, when it's running, it will construct dwarf DebugInfo and install it into the target binary. Now When you switch on DebugInfo by setting value 1 instead of the default 0, it doesn't just add dwarf DebugInfo, it also collects all the sources from the current build environment and populates a local source cache. It'll put it in the local directory sources with all the source files that you'll need to allow you to do source level debugging of the generated binary. Remember, when we produce the binary, we take all the classes that are in the class path, or in the local directory in this case, all the application classes. We take all the relevant JDK runtime classes that are in the Java release, and we take also all the substrate VM classes that provide equivalents to the JVM behavior and build all that into the native image, the target binary, and then throw away all those classes. So all the context that's around in this build environment that's used to actually build the image isn't going to be on the target runtime. And similarly, all the source files that we have available, for example, if we're picking things up from the Maven class path, we'll have a sources jar potentially for any of the classes that we're building. We've got source.zip files for all of the Graal classes that are in the class path that are added by native image, all the substrate VM code. We've got the JDK source.zip, which is sitting in the Java that's installed on this machine. All those sources are available here at build time, but they won't be available at runtime when we run that target binary. So the native image command collects all the necessary sources and caches them locally, and we can zip that up and then install it on the machine when we want to debug, and the debugger will be able to find all the relevant sources even though we don't have the build environment around. So when I run this won't just generate a local file called hello, a binary. It'll also populate that source cache, and we'll see how many files and how many classes actually go into the target image by looking at all the source files and seeing there's quite a lot of extra code, not just application code, but also JDK code and substrate code needed. Now I'm going to run this, and I'll just stop the video temporarily because it takes about 30 seconds. So when the video restarts, you'll see that I've run the command and it'll build the hello image. So as you can see, it's done quite a lot of work there. It's about 33 seconds. All the initial stages there are actually identifying the closed world of the application, and then there's a compile stage where it generates all the machine code, and then an image write stage where it writes the binary. Now what's added to that when we generate debug info is additional in the compile stage. There's a bit of extra work to track all the source locations for machine code and be able to generate a relevant source line information. And there's a bit of extra work in the image build and write stage where the dwarf debug info is added. So of those 33 seconds, probably about 3 seconds or so extra will be needed to produce the debug info. It doesn't really add a lot of overhead. It adds a lot more space, of course. It uses more memory. So in total we end up with 3.16 gigabytes of memory to model all the class space for the class world and then to generate the machine code. So we've probably added a few extra 100 megabytes of storage, and maybe up to half a gigabyte of storage at most to track all the debug info. When you look at the actual generated image, there's about 10 megabytes of image there. Now normally the image would be a lot smaller. It's been bloated with a lot of extra storage for the debug info. Well over half of that will be debug info. But of course that's not executable. That doesn't use any storage at runtime. The actual image footprint is much smaller than that, and so the memory use of the program isn't increased by adding this extra debug info to the binary. We've also got in the local directory, we've got a sources tree now populated, and there are 3 subdirectories. In the src directory we find the only application source hello.java. It's a single source program. In the Graal subdirectory there's a whole load of files that have been added. Let's look in the core directory. These are files for classes that are part of the substrate virtual machine. So for example, memory util is a class that's been compiled in because we do some new operations. Java main wrapper is a class which is used when the substrate VM starts up. The C entry point, the binary entry point, calls Java main wrapper, and that will actually call into the application main method, the hello main method. So there's a whole load of classes being added to provide underlying virtual machine capability. And in the JDK directory there's various various Java classes, JDK runtime classes. If we look at java.base in Java Lang, for example, we've got classes like system, we've got, say, math.java. So something is doing, probably the garbage collector is doing some arithmetic operations, it just needed routines from math. So in order to be able to debug the program, we need to be able to debug the math routines, and so the source file had been added to the cache. So we've got our cache of all the source files, we've got our binary. We could put this onto the target machine and then we could run the debugger to debug it. So let's run the debugger here locally. We'll use the local hello binary and we'll tell it about the source directories. So I'm going to set the directories path, which is where GDB goes to look for source files. So I'm telling GDB that source files can be found underneath the local sources directory src, local sources Graal, and local sources JDK. It now knows where to find source files. Let's have a look and see what files it knows, what classes it knows about. Let's look for any functions using the info command that contain the word main. So there's hello main. That's our entry point for the domain routine, and it's in file hello.java. And this directory sources/source does indeed contain a file hello.java. There's a method called big integer divide and remainder, and that's in file java base java math big integer.java. Well, that will be found under sources JDK. Notice it's indexed by the module name on Java 11. So the paths that have been included in the debug info that the debugger can find will be resolved relative to all these three source routes. So our source cache is being used to look up code and to find source files. So let's break hello : main. Let's actually stop in the main routine. And now you can see that the debugger knows what machine address that code is at, 405.600. It knows what file it belongs to, which it can resolve in the source cache, and it knows which line to stop at. If we run, there we go, we get to line 41. It's printed it out in the debugger window. It's also, because I'm running in Emacs, brought up a window showing us a little caret pointing at the current line we're at, so we can see where we are. If we do a backtrace, you'll see that we're in hello main at line 41, and we've had that call has been entered from a method of Java main wrapper run, which is the entry point for the binary that sets up the program state and then allows us to enter the Java main. It sets the virtual machine state and allows us to enter the main routine. If we step at this point, we'll step into that builder method, and there we are. We've moved to line 7 and we're about to create a new object, either a default greeter or a name greeter. Now let's see what happens. We just do the backtrace here. We've just made a step into a method. You can see it printed the new method we're in, and we've got an extra stack frame with the greeter method. We'll do a next step here and see what happens. Now we've switched file to object header impl. That's obviously something to do with creating the new object, and it's going to be constructing the tag word to go into the first header word of that object. But we've actually not made a method call here. If we do a backtrace, we're still in the greeter method, the builder method. But we've moved into file object header impl because this compiled method contains inline code. And so the code we're now executing, although it's inline in that compiled method, actually belongs to this source method. So we can see that the code that's actually inside this compile method is being assembled from lots of different bits of code, and we can track that in the debugger. This is constructing the tag. If we step again, we're getting an address. The address is the start of the thread local allocation buffer. Well, the current pointer into that buffer. This is a block of memory that's used for doing cheap object allocations. We then read the end of the TLAB. We add the size of the object to the top, and we see whether we've tripped off the end. If so, we need to get a new TLAB. If not, we can update the TLAB and use the initial pointer as the memory we use for the object. So that's what happens here. We'll come back to encoder's object header. This is jumping backwards and forwards because the compiler has reordered execution, so we're now back in encoder's object header. Now we're back in the TLAB allocation code. Now we're updating the top pointer, so we've used a slab of memory that's in the current TLAB for this object, and we've moved the pointer forwards beyond that object. Now we're going to do a write word, which will put the tag value into the first header of the object. Now this is a loop that initializes all the fields of the object, and we return that pointer as an object pointer, and we've constructed a default greeter. So we're stepping through this compiled code and we're seeing what the substrate VM is doing to actually implement that new operation. That means that we've got some idea of what's going on, what's really the application code, and what stuff that's being compiled in to implement virtual machine operations like memory allocation and so on. So if we step out of this, we can similarly step into the greet method. This is a virtual method dispatch, so we should end up, because this is a default greeter, we should end up in default greeter greet method. Indeed we do. Now if we step here, we can actually go into some of the JDK code. Here we are in print stream println. That synchronized operation, that's a sort of virtual machine JDK runtime operation. It actually has been implemented by some substrate code. We've gone into multi-threaded monitor support. If I come out of that by finishing the call, we've actually done the synchronization. We've now locked the system out print stream. Let's step into the print code and we'll actually step through some JVM code. We're in print stream write. It's going to call value of. We'll step into that. We're now in a string method. If I come back out of the value of call, we can now step back into write. And here we are, we've got a synchronization operation. We ensure the file's open, we write to the text stream, flush it, flush the character output stream that's underneath it, and then so on, we auto flush if needed. So here we are in ensure open. We'll jump back up and down to text.out. There's a sort of, some of the code is not quite in the right line, but we're doing all the operations in order. We flush the text buffer, we flush the character buffer, and there we go. When we did that character output buffer flush, we've got hello world appeared. So we've actually executed that write operation. If we finish it, come back out, we've done the print operation, and now if we step over the new line, we see a new line has been printed up here. So we've executed all the JDK code as expected, and we've gone straight into system.exit, so I finish that, the program exits. So let's go back to the presentation. We've got, summarizing here, we've got basic source level debugging, we've got line and we've got file and line breakpoints or method name breakpoints. We can run and then single step through application code, through JDK runtime code, through the virtual machine code for the substrate virtual machine that replaces the JVM. We can also step through inline code so we can see what's going on when code that we aren't expecting has been injected in, and we can track our way through all the execution of the source code as we do that and see the actual code in real time. Now clearly this is not going to be used by most end users, and certainly not used during development of a Java app. You would need to develop and test your Java application on OpenJDK first, where you've got a much richer debug environment, lots of tools and testing tools. But this will be used when you deploy an application if there's any problems in the deployed native image. Obviously you need to understand what the GraalVM JIT compiler and what the substrate virtual machine have done to modify the program to generate the image. You have to have some understanding of that. But imagine you have a situation where you run the program and test it on OpenJDK, everything runs fine. You run it as a native image and something goes wrong or something different happens. Now that could be because of a bug in the actual application source that manifests in native and not in OpenJDK. It could be because of a bug in the way that the native image generation is currently running, and there might be something has gone wrong there. Or it may actually even be a bug in OpenJDK that doesn't manifest in native image, but does manifest in OpenJDK, and so you get a difference in behavior. So this is a tool for identifying what will happen in what to do in those situations, and where the culprit is, whether it's the application, whether it's OpenJDK, whether it's the native image generation and the native image binary that's got the bug. So it's really very much an expert tool for support, for our support staff in particular, and for the support staff of anybody who's in Oracle who are using this, but it's also there for end users to use, and we hope that people who are willing to put a bit of understanding in and work out something about how Substrate and Graal work will be able to use this to debug problems in their program. It's clearly going to be something that most people will not use, but we think it's a really, really valuable thing to have for those rare situations where something goes wrong, and without it you really wouldn't be able to go any further. You wouldn't know what to do. Obviously we could make this a lot better. I mean, the clear thing that's missing is an awareness of classes or types. So the obvious thing is to embed the method info in a class definition, and the debugger knows that the methods belong to specific classes. We could define the layout of those classes so that the debugger knows that if you've got a pointer that belongs to a given class, then there's a certain size header and the fields are laid out in a certain order with given types of values in them, and then it can print the values field by field, either as object pointers, as addresses, or as numeric values, and so on. We would like to be able to also specify the name of those fields so that you can access fields symbolically using the normal syntax for getting a field value out of a reference. And that involves could include dereference chains, so that if you've got a pointer to a particular object of a given type, you can access a field, an embedded object field, an embedded field of that object, and so on. So you can work your way through the rat's nest of pointers symbolically. The same thing with static fields. It would be nice if static fields could be known about, could be referred to by class and field name, and the type was known, so they could be printed as primitive values or object values. You could print objects field by field. You could dereference field elements to other objects and so on, using field symbolic chains of solid field names. And similarly with parameter variables and local variables, it would be nice to be able to refer to those variables by name and have the debugger know that that value is currently stored in a register or is stored in a stack location, and be able to print the associated value, either a primitive value or an object, and then be able to dereference that and find object references into field values internally and so on, using chains that are rooted in a local variable name or a parameter name or a static field name. So that would be enough to really flesh this out and make it a much, much richer debugging experience, and we have plans to do all that at some point in the near future. So I hope that's given you a flavour of what's available now and where we're going with this. I'd really like anybody who's interested and brave enough to try this out and see, first of all, find usability issues and make us aware of them. Also, if there's something that's not working right, line numbers aren't correct, source files are not being found, it's not stepping in the right order, please let us know, and I'd be very keen to have bug reports from anybody who's using this. So thank you for watching, and I look forward to your feedback.